Hello, Science 10. Welcome to our second lesson in chemistry. Much like the first lesson on WHMIS, this is another very quick one as it is a review of stuff you've covered in grade 8 and grade 9, and we're going to review it again once again in grade 10. So what are we learning today? Today you're learning about classification of matter. So classifying matter into two very broad categories, known as pure substances and mixtures. And then from there, we're going to take our pure substances and classify them into elements and compounds. We're going to classify our mixtures as heterogeneous or homogeneous. Then we're going to practice. We're then going to look at who contributed to the model of the atom that we know today. So if you could follow along in your notes under lesson 2. So classification of matter. I would like you to be able to today make sure that you are able to give me definitions of pure substances, elements, and compounds, as well as homogeneous, heterogeneous, and come up with pictures and stuff like that that you can look at when we talk about them. So let's start with what is a pure substance. So if we look at the classification matter picture in your notes, it shows you kind of a flow chart of a pure substance, mixture, compound, element, and all that stuff. But what are they? So a pure substance is matter that is composed of only one type of particle. Now we have to be really careful because that type of particle can be a molecule or an atom. And when we look at this, what does that mean? Well, it means that it can be either an element or a compound. So let's classify an element first and kind of really look at what that means. So pure substances is only one type of particle. For example, an element. An element cannot be chemically broken down or taken into any other form or broken into different parts. It is just the element. And how do we know what an element is? Well, we have the trusty periodic table of elements. Yes, that's right. We love the periodic table of elements. If you know your periodic table of elements, if you know it's on there, you know it is a pure substance. Hydrogen, oxygen, fluorine, nitrogen, carbon, helium, tin, what else is there? Gold, silver, those kinds of things, right? I can't take any of those and break them down any further. They're just the element they are. In pure substances, though, we also have something known as a compound. Now, a compound is two or more elements put together, chemically bonded together. So when you take hydrogen and oxygen and put them together, or carbon, hydrogen, and oxygen and put them together, they're bonded together to make a chemical structure, okay? These chemical structures can usually be separated down by using something called a decomposition reaction, which essentially means we can break them apart. We're going to learn about decomposition reactions later on in this year, in chemistry. So what does that mean is an example of a compound would be water, H2O. You guys are probably very familiar with H2O. And this breaks down into oxygen gas and hydrogen gas. You can actually separate the two. Same with something like glucose, C6H12O6. You can chemically break apart glucose and put carbon back onto carbon dioxide, which can be broken into carbon and oxygen. You can take the hydrogen and put it back on water. You can take the oxygen and put it back on water. So we can chemically break down compounds. But the thing is it is a compound because it's two or more elements. So therefore it's a pure substance because again, it's only comprised of one type of particle. Water is water. Okay, so that's your two different categories underneath pure substance. So let's move on to the next one in your notes, which is known as mixtures. So mixtures are now a combination of two or more pure substances. So kind of think of it as taking like water and salt. Water is a pure substance, H2O. Salt is a pure substance, NaCl, and we're mixing them together. That's a mixture, okay? This is because they retain their own chemical and physical properties, meaning water will remain as water and salt will remain as salt, okay? So if I mix the two together, I make salt water, but if I was to take it and look at it at the molecular level and be able to see all the different particles, I would see water particles and salt particles. They're still their own chemical structures. So we're going to start in your notes, heterogeneous is first, but let's jump down to homogeneous. So homogeneous has no visible divisions. The root word homo means similar, okay? Homo sapiens are humans. We're all similar, okay? That's the root word there. So it has no visible divisions. We also call it a solution, and it looks very uniform throughout, meaning something like Kool-Aid or salt water. When you take water and some sort of substance and mix it together and it looks like one thing, that is a solution, it is homogeneous. All right. On the flip side, we have something called heterogeneous mixtures, and that essentially means it has visible divisions. Each thing has its own uniform property, but it's mixed together, but you can see the distinct parts, much like chili that I make. I love chili. It's delicious. Okay. But in it, you have meat, beans, corn, sometimes peppers, different varieties of beans, maybe some canned tomatoes. You can see all those parts, but it's all in one pot. It's all mixed together, and that is heterogeneous. So at this moment, I want you to take a few seconds to practice the activity of classification matter in your notes. There's gummy bears, Cheerios, limestone, tea, sulfur. We're going to go through it together as a class and do a little review, but I want you to try it on your own first, classifying it as either a pure substance, element, compound, or a mixture, homogeneous or heterogeneous. So give it a try. Moving on, now that you have completed your practice, we're going to talk about the atomic theories. This again, guys, is review from last year. There's a video that I probably played if you were in my class multiple times. Be prepared to see it again. So who did what and when? Dalton. Okay, so 1808. Good old John Dalton. Now, John Dalton, this is a pretty portrait right there. He decided that all matter is made up of small particles called atoms, and that you cannot create, destroy, or divide these atoms. That was a big part of it. They're just the way they are. You can't do anything to them. He also said that every element, all atoms of an element are identical, but different elements have different atoms. All right, now that might be confusing, but as we get talking about elements, you'll see what we mean there. He also said that if a compound is formed when atoms of elements combine into fixed ratios. So again, H2O is a fixed ratio. That makes water. H2O2 makes hydrogen peroxide. Don't drink it, you'll die. Okay? So compounds are formed out of atoms of elements, but they have to be in fixed ratios to make those compounds work. He also said chemical reactions change the way atoms are grouped, but not the actual atoms themselves. So if you look at the process of photosynthesis, carbon dioxide plus water plus energy gives us oxygen and glucose, okay? That's a chemical reaction. Now, the way those carbons, hydrogens, oxygens are grouped is different on each side of the equations, but the atoms themselves are not changed. So the carbon atom does not get changed. The hydrogen atom does not get changed. They stay the same. So essentially, to summarize good old Dalton stuff, is he summarized that we view atoms as a sphere, and you can combine them in different ways to form different matter. We call his model the billiard ball model. Okay, some balls are bigger than the other, some are smaller, hydrogen, oxygen, those kinds of things. So Dalton was kind of the reigning theory for a very long time until 1994. 1894, when J.J. Thomson, which I spelled his name wrong, found cathode rays. So he didn't find cathode rays. He took cathode rays and shot them and kind of figured out, hey, I think there's this kind of negatively charged particle in amongst these spheres. So he formed the atomic model, which we would call the plum pudding model. I call it the chocolate chip cookie because if you look at the picture, it kind of looks like a chocolate chip cookie, where essentially what he said is that negative electrons, that's the small silver ones floating around in that big green ball, are just surrounded, okay, by a very positive particle soup or a very positive particle sphere. And that was kind of his big contribution, is he said that there are something called electrons. Now, in your notes, you do not have the picture of Thomson's model of the atom. Please add it beside your last sentence, which is negative electrons in a positive particle soup. So just add it because we are going to need to know what the theory's pictures look like. Now we're going to talk about our good friend Rutherford. So a few years later in 1909, Rutherford came along and he took these really tiny small particles called alpha particles and he shot them at gold foil, really, really, really thin foil made out of pure gold. And theoretically, all of these particles, since they're so tiny, should travel through it and there should be no issues. But what he found, because he had all these fancy equipment, is that sometimes when he shot an alpha particle, it actually bounced back from hitting something. So he reasoned that instead of it being a positive mass that the electrons are in, it's actually going to be a very dense core. So he's like, instead of it being all around, there's just this really tight core in the center and the electrons are outside of it. He called that core the nucleus. And he said the electrons are orbiting it much like the planets orbit the sun. So we sometimes call his theory the planetary model. Okay. And this is really important because he came up with this idea that every atom should have a center and that these electrons float around it. He pretty much said that it's an empty space, but then the really important part here was he looked at different elements like helium and hydrogen, and he actually kind of weighed them the best he could, and he compared the mass. And what we know now, which was novel when he did it, was that they don't weigh the same. So what he ended up figuring out is there's actually another particle in there that is actually the weight of the atom, and we call that the neutron. So he gave us the nucleus and the neutron. The last gentleman I would like to talk about is Niels Bohr, and he's going to become pretty important in our movement through the first part of Science 10 here. So you guys may remember him because we did a couple Bohr models, which we're going to do more of here shortly. So he came up with that. Now there's a nucleus. Electrons are on the outside, but the electrons don't just hang out. They have to occupy a special space. And so he called that special space energy levels. And he said that electrons can actually move between those energy levels, giving off or taking in energy. He said emitting or absorbing energy, and it moved them between energy levels. That's going to be important when we talk about ionization and ions. Now, what ends up happening is he just says that electrons can't just exist between energy levels. It's distinct. They have to be in an energy level, and every energy level can only support a certain number of electrons. So, for example, energy level 1 can only have 2, and then 2, 3, and 4 can have all 8 amount of electrons, okay? So essentially think of it like this. If you live in a city and you live in a really big city and you live downtown, you're gonna live in an apartment probably. There's no houses downtown. Those apartments are really tiny. The only amount of people you're gonna fit in is about 2 people in that apartment comfortably. But as you move away from the center of the city or the nucleus and you buy a bigger house, you can fit more people in it. So the next level you can fit are 8 people. Now for the level that we are going to discuss in Science 10, it will be 8 the whole way through. So level 2, 3, and 4, the maximum amount of electrons that you can have is 8. We call those electrons valence electrons. And when they are full, we call that having a full octet, which we're going to talk about more shortly. So now we're up to what does it look like now? Now, the picture you see here is more of the thing we see from the Big Bang Theory. It's very much just the one that we recognize, but this wouldn't be ideally the right one. This looks more like Rutherford's idea with the electrons circling the center of the nucleus, making it the planetary model, but this is kind of the model that we have seen more or less, okay? So we have now is protons, neutrons are working together in the nucleus for the positive core, and electrons occupy the space on the outside. So for your understanding, that's where we are with the atom. So what did you learn today? You should have learned the 2 broad categories, pure substances, mixtures. You should have learned in pure substances, there's elements and compounds and what the difference is between them and how to classify them. You should have learned heterogeneous and homogeneous in mixtures, differences, how to classify. And lastly, who contributed to what we know today about the atom. So ladies and gentlemen, please make sure you have everything in your notes, and I will talk to you soon.